I welcome you all to the Spark Research YouTube channel. This is Dr. Virchandra, Assistant Professor in the Department of ECE, and in this session we are going to take the contents from this course, Analog and Digital Communication. And this is the last session of this syllabus of this course. And in this session we are going to take the contents from the fifth unit, and this is the second part. So here we are going to talk about the information theory and the channel capacity. Particularly, we will focus on these topics like Shannon coding and then the mutual information and the channel capacity theorem. So these are the important points that we are going to tackle in this session. So here is the syllabus. If we look into the syllabus of this fifth unit, here we are going to talk about the entropy, information theory, and already we have discussed about the Huffman code also. So these things we have discussed, and in this session we are going to take the Shannon and your mutual information. That is one of the important topics, and then the Shannon channel capacity. Okay. So if you want to visit the Huffman coding and entropy and the information theory, you can visit the previous session. Okay, so let's start. Question first is that what is this Shannon coding? So an algorithm technique for variable length source coding based on the symbol probabilities, right? And what is the objective? So objective is to reduce the average code length. Like suppose if symbol A is written by the code word like three code words, so our objective is to reduce. So here we are going to use the only two code word to represent the A. Similarly, another information, the symbol B is there. So again, suppose the three code words were there, so here we are going to use the only two code words. So our objective is to compress the data so that we can use the less number of code words or less number of the bits to represent the same information. So that is our objective. Right. Now question is that how we'll do. So here like suppose we have these information A, B, C, D, E. So what we'll do, we will divide into the two teams, right? One team may contains the AB information, another team may contains the CD information. So team 1 we will assign a 1 value, that is 0, and team 2 we will assign another value like 1. Again we will keep on dividing these since in the team second how many members, 3 members. So again we will divide and we will keep on assigning till the last variable we reached, right? So this is the technique only. We will look into that in the details with the examples that how can we assign the particular values and how we will divide the team. Okay, so average code word length versus the source entropy efficiency graph is here. So you can see here the whenever the average code word length is the less, the entropy will be less. So here how we'll find out the entropy, and you can find out the average code word length, and then you can find the efficiency. So our target is to increase the efficiency. So we will see how to find the entropy and how to find the code word length so that we can find out the efficiency. So let's take an example here. Before taking the example, let's have some discussion over the Shannon coding. So in Shannon coding, symbols are arranged in order for most probable to least probable, right? So this is the technique. So first we will arrange the maximum probabilities values, then in the descending order we have to arrange, right? And then we will divide into the two teams, right? Team 1 and team 2, and then means we will divide in such a way so that team 1 have the total probabilities equal to, almost equal to, not equal to, maybe very closer or nearly equal to the probabilities of the addition of the team 2 probabilities, right? All symbols then have the first digit we will assign one value, that is 0, and another team will assign by the another value like 1. Okay, as long as any set with the more than one member remain, this process will continue till once we'll assign a independent one specific value, that is 0 or 1 to all the probabilities, then it will end, right? And after assigning one, how will write the final code patterns. So when set has been reduced the symbol, of course this means the symbol code is complete, and then we will will reach to the path in left to right, and we will write the code from right to left so that we can find the final code patterns. We will look into the example here. Okay, So, Sarin-Fanot theorem states that a given noisy channel with the channel capacity C and the mutual information transmitted at a R, then if R is less than C, there exists code that allows the probability of error at the receiver to be made arbitrarily as small. So, and then the converse is also important. If R is greater than C, then arbitrarily a small probability of error is not achievable, right? Okay. So here is the example. Here exactly this is one of the important things. So let's take the total. How many symbols are there? S0 to S5. So total 1, 2, 3, 4, 5, 6. So total how many symbols are there? Total 6 symbols are there. Each symbols have the probabilities like given 0.3, 0.25, 0.2, 0.12 and 0.08 and 0.05. So probabilities are given and already it has arranged in the descending order. So if it is the random values are given, then you may arrange it, right? Then we will divide the teams. So team 1, like see, suppose if we are considering this boundary, right here, if we are considering the boundary, so just check the values of the probabilities above to this boundary and below to this boundary. Is this equal or not? So if you'll see now, then addition of these first two is 0.55 and addition of these remaining, so 20, 32, then 40, 45. So 45 and 55, so closer to each other. But if you like put only one and the remaining five, then what will happen? This will 0 point the 30, and these remainings will become 0.65. So gap is very large. So that is why we will consider team 1 which have the 0.55 and team 2 which have the probabilities of the 0.45 additive values, right? So then both team will be almost equal to each other, right? So then after dividing this boundary, our objective is to identify this boundary. Which boundary? So that the addition of the probabilities of the team 1 should be equal or closer to the addition of the probabilities of team 2, right? After finding the team 1 can be assigned by 0 and team 2 can be assigned by the 1, all the values, right? All the patterns. So once if we got this how to find the team 1, team 2, then we will keep on finding, we'll keep on dividing the team for individual one. So for team 1, now if you'll see, only there are how many members? 2 members. So we'll divide it as simple, means one will be the 0 and one will be the 1. But in the second team, now if you'll see, there are how many members? Total 4 members. So 4 members means again we have to divide the team. So how will divide? Now here see, here the probabilities of this is how much? 0.20, and what is the remaining probabilities? So remaining may have the addition of almost 25. So 25 and 20 almost equal, right? But if we'll consider in between half, then here it will be 32, here it is only 13. So gap is very high. So here what we'll do? We will divide the team from here. So team 1 is assigned by 0 and again team 2 assigned by the 1. Okay, similarly we'll continue, again we will divide. So here the third division, here this division how we are doing? Team 1 we are having the probabilities 12 and team 2 have the 13. So both are almost same. If we'll keep these and these two both are in one team, then it will 20 and it will be only 5. So gap is very high, so that is why we are keeping this one alone, right? So this is alone only, and so that our team will divide it. So after dividing this team, again we will assign 0 and 1 1, and at the end, like now finally you have only 2 members, so divide into the 0 and 1. Now you have to write the pattern. So how will you write the pattern? So exactly 0 0, so 0 0, 0 1, so 0 1, and 1 0 1 0 and 1 1. So whatever the bit patterns you got. So now code word length you can find here, the how many code word we are using here: 2, then 2, then 2, then 3, then 4 and 4, right? Okay, so further you can find out the efficiency also. So L, that is the average code word length, we can find the probability into the code word length. So for the probability first, the probability probability was 0.30 and code word we have found 0 0, right? So 0 0 means 2 members, so that is why we are multiplying by 2. Second one have the probability 0.25 and how many members? 2 members. Similarly we can assign the same bit patterns, and we can find out the average code word length. After finding the average code word length, you can also find out the entropy. So how will you find the entropy? In formula is that h of x is equal to how much? Probability into log of 1 over probability. So this is the formula. So here probability is given how much? For first information, first symbol 0.3, and log of 1 by 0.3, same probability. So put that and put the for the same for the all the information, you will get the entropy. So there is no change in the entropy. Entropy is same whatever based on the probabilities. Here the average code word length we will modify because of the Sun and Fano, because now the bit patterns we are using the less bit pattern, right? So average code word length will be changed, and further efficiency you can find entropy divided by the average code word length. So you may get the 99.15%. So this is exactly way to solve the question related to the same. Okay, so now let's talk about the something like mutual information. So what is this mutual information? So mutual information is the information your the content by the mutually, like mutual information is the quantity, is the amount of the shared information between channel or variables, right? Suppose here is h of x and here is h of y, then what will be the mutual information? I x semicolon y. So how can we represent it? So this mutual information can be expressed by this expression. So this is one of the very much important equation, that is reduction in the uncertainty. So what is that equation? I of x semicolon y, that is mutual information, is equal to h of x minus of h of x conditional y, right? So this is the technique to find the mutual information. And like this is the in mutual information, here the total entropy is h of x, so just remove this h of x y, right? So then the rest amount we will get, so that one mutual information that is common in both at h of x and h of y, so like that you can say also. So and also the one extended the version of this mutual information, you can also use this expression, that is mutual information equal to h of x, h of y, and minus of h of x comma y. This is also the expanded version, so we look into that. Okay, so mutual information is here you can see the mutual information is a measure of the uncertainty about the channel input, which is resolved by observing the channel input, and this expression is alone is a very much important, right? So this is called the mutual information, where I of x y is equal to h of x, this is the entropy of x, and this is h of x of y, so that is entropy of x over y. And how will you find the entropy of x over y? So we are going to fix the y is equal to y of k. So y of k is a particular random variable that will take the value y is equal to k, corresponding to the probability whatever the h of x will be there. So you can find out using this. Okay, property is there. So property I of xy is equal to I of y of x. So this is the property only. Okay, so channel is symmetric, this is called the symmetric, and you can try to prove this also. So how will you prove? So we'll start from the entropy, right? So entropy, already you know entropy, how to find p of x plus into log of 1 over p of x, and here we are considering the nth number of the x variable. So you can consider j is equal to 0 to 1. So add all those information. Further use the Bayes theorem, Bayes rules for conditional probabilities, and then you will get the values of that will be equal to y of x semicolon y. So this is the symmetry property. Similarly, non-negativity, that will tell you that mutual information never be the negative value, always it will be minimum, it will be zero, right? Means we cannot lose the information on the average by observing the output of a channel, right? So here this is the conclusion of this non-negativity. Similarly, one of the more expansion, this is the also one of the very important equation that you can remember. that is I of x y is equal to h of x plus h of y minus of h of x y. So this is the expansion version of the mutual information. This is also one of the important equation. If you remember, I of xy is equal to h of x minus of h of x over y, and that was the one of the primary equation, and this is also the important equation. So you can see here the proof here, that is how to find. You can, again we will start from the entropy only for the both the one, and then you can replace the values and you will get the final equation that we need. So this is actually the measure part. Then the channel capacity of a discrete memory relay. So what is the channel capacity? So if you got the the information, that is the maximum information, so mutual, if you understand the mutual information, suppose mutual information will tell you, like suppose these are the inputs and we are going to fix the inputs, that is x1, so corresponding to x1, now the the probability of y has been fixed, either y1 y2 y3 or like that. So corresponding to, so this is the conditional probability. So because of that we are going, so that is the mutual information, that is we are going to fix a one input or one output, corresponding to that probability will be fixed. So that is why this common part, which is common in both h of x and h of y, so common part is mutual information. Already we have discussed all this information, that is mutual information. So here the maximum possible value of the mutual information is the channel capacity, that's all, right? So how we'll find? So here this is the formula. Already we have seen the mutual information, that is h of x minus of h of y. So just that is the maximum possibilities values, that will be the channel capacity. Okay. So here the same things, channel cap here I of xy, that in terms of the entropy, and so that is p of x and log of 1 over p of x. So we have already seen that is how to find the information, that is mutual information. So same equation we are going to use it here. So our target is to maximize this information, and so that is why this is the channel capacity. Okay, so we'll look that how exactly we'll get. So channel capacity of a discrete memory-less channel, commonly denoted by C, is defined by the maximum mutual information in any single use of the channel signaling, where the maximization is overall the possible input probability distribution. And then for a specific case, so a specific case is your binary symmetric channel. So in that case what will happen, the same informations, that is channel capacity, will be emerged as like C is equal to 1 minus h of p. So how? So here, so channel capacity C is the nothing, your maximum I max, and here px0 and px1 both will be half, right? Means in the mutual information, because we are considering only two inputs. So t input means p of x of 0 means probability of 0 and probability of 1, suppose both are equal, then in that case it will be half, right? And so probability of one conditional, you will, if you'll consider as a p, then other y by x naught will be the 1 over 1 minus p, right? So once you will put that values, like in order to calculate the entropy, so p of log of 1 of p and plus 1 minus p and log of 1 of p. So if you solve, you will get the channel capacity. Here is the transitional probability in between 0 to 1 for this the binary inputs. So you can see here the inputs are varying from 0 to 0.5 and 0.5 to 1. Okay, so this is the channel capacity of a binary symmetric with the transition probability p. So this is the final equation, which is very important, channel capacity theorem, that is C is equal to B log 2 1 plus SNR, that is channel capacity is equal to bandwidth into log of 2 and 1 plus SNR. SNR is the signal to noise power ratio. So this is the most important equation that you should always remember, where C is the channel capacity, B is the bandwidth, and S by N is nothing, your SNR. So here suppose you are transmitting the some masses and you are receiving the some masses. So here may be the your channel. So this may be the noisy signal. So what will be the capacity for this channel? So that will tell you by this, right? So this is the limitation of your channel capacity. Okay, so how we'll find out? So let's see the equation how to derive it. So here C is nothing, channel capacity. Already we know the maximum of I of xy. And what is this I of xy? So this is nothing, the mutual information, that is h of your y and minus of h of y over k. So already we have seen how to find the mu of mutual information. So our target is to find this one, and and here we will target to find h of y over k also. So we will find out this one also, and then we will put. So here if we'll put the same equation, so here like you can modify this one, and so since h of y divided by xk will be h of nk, so we will find the nk and then we will put it in the final equation, and then we will get the this values. So this, and we are considering the standard Gaussian noise only. So in that case, the the for noise power and the signal power, you can write in the terms of the variance here. So after finding the variance, you can put it the values, and you will get the channel capacity, that is half of log of 2 and 1 plus p of sigma square. So this is the final and values. So this is the very much important equation. Always it will be used, so you can remember. So channel capacity is equal to bandwidth into log of 2 plus 1 plus SNR. So as signal to noise ratio. Right. So very important equation. Okay. So further you can plot the graph in between the your bandwidth efficiency, like bandwidth efficiency. You can find out and the channel capacity. So like SNR value is on the, and then bandwidth efficiency, how much will be. So you can see here efficiency is higher if a region RB is greater than C, and channel capacity boundary for RB is equal to C. So this is the boundary, right? So you can put the values of your C and B and the SNR. You can plot, since logarithmic is there, so here it will looks like the logarithmic type of the equation. Okay. So that's all in this session. Thank you to join. If you have any doubts, please drop your comments.